everyone, and welcome to this talk where I will show you the results of an experimental comparison of a few different tuning strategies for Linux KVM virtual machine. My name is Dario. I work for SUSE on virtualization, and here in this slide you can find some information about myself, but let's not waste too much time on that and jump right into the topic. Yay! There are a lot of things that we can do to try to achieve the best possible performance inside one or more VMs. Huge pages, vCPU pinning, memory pinning, and more. Due to time reasons, I won't go into details of any of them, but a lot can be found in documentation or online, including other talks by myself at other events. So, how do we tune virtual machines? Well, we can do it at the hypervisor level, which is very powerful, but it's also very long and complex and not very flexible because we must know and specify a lot of details about both the VMs and the host. Alternatively, we can rely on some form of middleware, such as, for example, KubeVirt. But then the complexities move into the interfaces and the implementation of the middleware itself, and there have been examples already of that having been done wrong, and you don't have much control. So tuning is complex. Let's check the experiments I've done to see if such complexity is worth it. Okay, as a host, I used a rather large Intel server with 384 physical CPUs, 4 NUMA nodes, and 2 terabytes of RAM. The VMs instead had 4 virtual CPUs and 12 gigabytes of RAM each, and the number of concurrently running VMs varied between 1 and 192. So, until there are fewer than 96 VMs running concurrently, the host can be considered underloaded. When there are exactly 96 VMs, the host is working at capacity. And when there are more than 96 VMs, the host is overloaded. Of course, that also depends on what the virtual machines are actually doing. So it depends on the benchmarks. And the benchmarks that I ran inside of each VM were Sysbench CPU, a purely CPU-intensive benchmark, and I made multiple runs of it with a different number of active threads. Sysbench OLTP, a database benchmark, also with different number of active threads. And then I tried to investigate latency by using cyclic test, either running alone or together with some background noise provided by CardBench. By the way, all the results that you will see have been obtained using CFS as the CPU scheduler, both on the host and in the VMs. Now, we'll soon have EVDF, a new scheduler, and of course there's no guarantee that the results will be the same with it. So I guess thanks, Peter, for that. Yeah, thanks. No, actually, I mean it. Thanks, because that also means that I can just run all these experiments with the new scheduler, and I already have a talk for P99 Conf next year. But yeah, anyway, let's see which tuning configurations I considered. So the first one, I'm calling it default, involves no tuning at all. No pinning of virtual CPUs, no virtual topology for the VMs, no pinning of the memory, and AutoNUMA was left enabled on the host. For the pin vCPUs to node case, instead, I was only pinning the virtual CPUs of each VM to a specific NUMA node. It can be seen as a form of relaxed pinning, and AutoNUMA was kept enabled. In the pin mem to node configuration, it was the memory of each VM that the only thing that was pinned to a specific NUMA node, to see if we can get AutoNUMA to pull the vCPUs there as well. Then there was the pin vCPUs to core case, where I pinned all the vCPUs of each VM onto a specific set of cores of the host. So this is not yet one-to-one pinning, but it's definitely stricter than the previous one. Pin vCPUs to core plus mem to node, it's basically the same as before, with the memory also pinned to the proper NUMA node, and AutoNUMA is now disabled. And then there is pin vCPUs one-to-one plus topology, where not only vCPUs were pinned one-to-one to vCPUs, and memory was pinned to the respective node, but a virtual topology for the VM was also defined. This is the configuration with the most tuning applied. So it's kind of the one that we would assume will perform best pretty much under all circumstances, isn't it? Well, let's see if that is really the case. Yeah, let's see. So let's start with the results of Sysbench CPU. Each one of these plots is relative to a specific number of concurrently running VMs. And what is varied on the x shown on the x-axis is the number of threads for the benchmark. So basically the load inside of the guests. Until the system is underloaded, all graphs are very similar. We see that the configuration that include strict pinning, the configurations that include all of them, strict pinning saturates earlier. And this is due to hyperthreading, and it was expected, since in these cases, the host scheduler is not able to spread the load among cores due to pinning itself. Increasing the number of VMs, the gap between unpinned, relaxed pinning, and strict pinning becomes smaller and smaller. And that also makes sense. Something interesting to note, though, is that even when we are at capacity or in overload, the fully tuned configuration is actually not the best performing one. And this is slightly, at least, unexpected for me, considering that this is a pure CPU benchmark, and I'm trying to investigate more thoroughly what's the reason for that. And yeah, here in this slide you see basically a subset of the same results, only shown differently. So these graphs here, in each one of them, we have fixed the number of threads used by the benchmark inside of the VMs, and we look at what happens when we when we increase the number of VMs. Okay, let's have a look now at how stable and consistent the numbers are still for Sysbench CPU across all VMs by checking the standard deviation among all the results from all VMs. When the system is under high load, the stricter the pinning, the more consistent the performance are, which is exactly what we would have expected, I guess. When we are underloaded, however, if a form of pinning that is not one-to-one and also includes virtual topology is used, the results are less stable, but they are also less stable than relaxed pinning and even of no pinning and no tuning at all, which is interesting in my opinion. But yeah, apparently, even if full tuning is not able to give us the best average performance for this workload, at least, it is actually what we want if we need stable and consistent results, which is a good thing. Okay, this one here now is Sysbench OLTP, the database workload. And we can see again that in terms of average performance, the fully tuned config is not really the best performing one. Actually, when just one thread is used by the benchmark, which means the system is underloaded even with 192 VMs, it's almost the worst performing one. When load increases, teams become a bit better for it, but even at max load, it's slower than relaxed pinning, and even of no pinning at all. This is probably due to the fact that the benchmark does not keep all the vCPUs of all the VMs always busy all the time, like Sysbench CPU does, not even with 6 threads. And apparently leaving to the host scheduler some leeway for moving the vCPUs around is better in this case. And also the fact that default is similar to pin vCPUs to node seems to suggest that it does a decent job at that, even without any tuning hints from us. Well, at least the one-to-one pinning configuration is better than the other strict pinning strategies. It's also interesting to note that for this workload, with the fully tuned configuration, performance seems to not vary much when more VMs are active on the host. That's nice. So as far as standard deviation is concerned for Sysbench LTP, as it was already for Sysbench CPU, aggressive tuning pays back, especially under load. Check, for example, the graph for 6 benchmark threads. Default and pin vCPUs to node, which were our winner for the average performance, are, however, not too bad until we don't overload the host. But yeah, as soon as we do, stddev explodes. Last but not least, latency with cyclic test. The top graph seems to tell us that best average wake-up latency can be achieved by pinning the vCPUs. Doesn't matter much if we pin them to cores or one-to-one, and neither it matters if we tune more, for instance, with virtual topology. Looking at maximum latency, however, we see that one-to-one pinning is by far the winner, especially when there are a lot of VMs. Check though how bad they are the other strict pinning based configurations, and check how not too bad default is again, although it degrades fast with when load increases. And that was for cyclic test running alone in the VMs. What happens if we add background noise using kernbench also in each VM? Well, it seems that as soon as we reach overload, leaving the system be and not disturbing it with our tuning would be the way to go in terms of average latency, at least, which is weird and interesting. Although, I mean, it's probably because kernbench, even if it's a CPU intensive activity, it's not a benchmark in this case, isn't just hogging all the vCPUs of all the VMs all the time, but it's, again, quite interesting in my opinion. For maximum latency instead, one-to-one pinning wins, which is reassuring to see. So, can we draw any conclusions? Well, to me, it looks like we can say that whether or not it is worth to embark in the complex endeavor of tuning your VMs, surprise, surprise, depends on a number of factors. It depends on the workload, which is something that we could have expected and that we knew already. But it also seems to depend quite a bit on what's the typical load that we expect to have on the host. And it also depends on the metric that we are the most interested in. At the very least, it seems that we can say and conclude that strictly partitioning the host and going heavy on tuning of the VMs with one-to-one pinning, virtual topology, and all the other stuff gives us the most consistent and and the best worst case performance. Unfortunately, it doesn't really guarantee the best average performance too. It does reasonably well when the system is experiencing heavy overload, for example, which is good, but likely heavy overload is going to be an edge case. And this fully tuned config definitely does not do its best, again, in terms of average performance when we are underloaded or at capacity. For the future, I think that you can say that the relaxed pinning configuration showed some potential at least, and therefore I'm thinking to try to dig more into that direction by trying, for example, to combine it with the other tuning measures that we have available, like the topology, for example. And I also would be interested in trying some uh, mixes between strict and relaxed pinning. And yeah, this is all I have. So thanks again for attending the talk and goodbye. Bye.